Can you see my screen? Yeah, on the stream on YouTube. Oh, the empty board, but yeah. Okay. I didn't put any delay on it. Okay. Anyways, I'm gonna start now. There's no delay. Oh wait, yeah, because that was like the weird like preview shit. Um. Oh, maybe it's just laggy. Oh well. Anyways, I'm gonna start now. So hello everyone, welcome to my first live lecture on statistical mechanics. Sorry that the first video was a bit of a jump into all the maths. I'll try stay away from all of that for today. But anyways, for now I'm going to talk a bit about statistical mechanics and start this series off on physical chemistry. Today my goals are just to go through the physics behind what's going on, and then in the next episode we'll get to doing calculations for the partition function and then equilibrium constants, getting into a bit more of chemistry. So anyways, our starting point for statistical mechanics and thermodynamics will be the internal energy U. And so this is just going to be the sum of the kinetic and potential energies of our system. So this is going to be equal to EK plus what I'm going to call V for potential. And I can express V. V is going to be the chemical potential in this case, and it's going to be equal to the sum of mu I n I. And here mu is the chemical potential energy that a particle of type I has, and ni is the number of those particles I have. And then the kinetic energy, well, is equal to like the sum of half mv squared for all of my particles. So anyways, if we were to consider a small change in U, the different ways I could change the internal energy of my system, first of all, there are the ways I could change the potential energy, and so that's due to changing the number of each type of particle in my system. And so this term for the change in chemical potentials is just going to be mu I d ni. And then in terms of the kinetic energy of my system, I could do two things. I could make the stuff in my system do work, or I could heat up my system. And so I'm going to subtract dW for the amount of work my system does, and I'm going to add I'm going to add delta Q for a small amount of heat I'm going to put in. So anyways, looking at this dW term, we're going to see that this is going to be equal to P, the pressure that my gas is going to exert, multiplied by dV, a small change in volume I have. And this is because if I've got a box and I increase its size by some small amount, dl, and my particle is exerting a force, F, then the work my system is doing is going to be equal to F dl. And so if I want to work out the force, I can have force is equal to pressure times area, sub that in, so now dW is equal to PA dl, and area times my change in length is just going to be an overall change in volume, so that's equal to P dV. So anyways, now I've got that, and I want to talk a bit about what heat is, what temperature is, and then also introduce concepts of entropy, like microstates and statistical mechanics as a whole. And so to start off, I'm going to say that a system is in a given microstate psi, and psi is going to hold all the information about the momentum and the position of each of my particles, and so it's going to have a lot of different dimensions. It's going to contain a lot of information, and so it's not particularly a very useful thing to have. but psi is a possible state in my system, and it's going to have various macroscopic properties describing this microstate. And so, for example, we can get the total energy of the system. What's often useful to do, and we'll use it for all our discussions, is to say, is to instead talk about epsilon, where epsilon is energy subtracted by some constant epsilon naught, which represents the lowest possible energy the system could have, which often is not equal to 0, as we'll cover. But anyways, say we wanted to look at a probability distribution of all of these microstates, which is the Boltzmann distribution, which we're going to derive. And so to start this derivation, we're going to have a box, and the box is going to have a total energy of epsilon, and then inside of it, I've got a smaller subsystem, which is closed, so it can't exchange particles with the surrounding, but it can exchange energy. And so this smaller box is going to be in a microstate, psi I, and so it's going to have a corresponding energy, EI. And so the energy of the reservoir, which I'm just going to call E res, so everywhere outside, oh, sorry, these should be epsilons, is simply going to be equal to epsilon minus epsilon I. So the total energy is equal to just epsilon. And so to work out the probability that the system is in a state psi I, since this is fixed, it's all about the different ways I could get but my reservoir to have an energy epsilon res. And so I'm going to define omega of epsilon to be equal to the number of ways that my system can be in a state. And my first sort of hypothesis about statistical mechanics, and one of the two assumptions I'm going to make sort of axiomatically, is going to be that at equilibrium, my system, each of my possible states with the same energy are going to be equally likely. And so in the end, it turns out that the probability of psi I is just going to be proportional to omega of epsilon res. And of course, this was equal to epsilon minus epsilon I. Now anyways, omega is all about counting. And so it's probably going to have some factorials in it, some exponents in it. And so if you were to graph omega of epsilon against epsilon, you would probably find it shoots up very, very quickly. And so if we were to consider the logarithm of omega of epsilon, right? So we said it's probably got some factorials in it, or some exponents in it. So if you've got this is approximately equal to epsilon factorial, right? The logarithm of it, we're going to approximate using Stirling's approximation, which is just a mathematical result I'm going to give you, and it's the logarithm of x factorial is approximately equal to epsilon x minus x. And so this is going to tend to epsilon, then epsilon minus epsilon in this case. This is just a trial function. This isn't actually what omega is equal to. But we're going to find that when epsilon is very big, since the logarithm doesn't change that much, for large epsilon, this is going to look roughly like a straight line with a very slowly increasing gradient. And so what we can do is approximate this as a straight line of the form. So if I've got a point here, right, we're going to say this is equal to, so this is at epsilon, right? So if I've got ln, if I've got omega of epsilon right? I'm going to call this alpha, and then I'm going some distance epsilon I away from this when I'm subtracting epsilon I here, and so I can subtract beta times epsilon I, where alpha is the height at this point, and then beta is the gradient of my slope. So this is that. So anyways, since we said that our probability was going to be proportional to, well, is going to be the exponent of this, we're going to find that psi I is going to be proportional to the exponent of alpha minus beta epsilon I. And so using some index rules, we can bring out this e to the alpha here as a product. And since this is a constant, we can divide by it and absorb it into the proportion. And so in the end, we get the probability distribution psi I is equal to 1 over q times e to the negative beta epsilon I. And here 1 over q is a normalization constant to ensure that the total probability is equal to 1. And so q is going to take the form of the sum of all of the e to the negative beta ei's that I could have. So this is the Boltzmann distribution. Oh, this is the probability that I'm in a state psi I. And so with this, we can look at the probabilities of each of these microstates. And first of all, I guess I should define beta. This is the second axiom I'm going to have in my assumptions, and that is going to be beta is equal to 1 over kbt. Kb here is the Boltzmann constant. It is chosen so that the average kinetic energy of a particle in a gas is equal to 3 over 2 kbt. But anyways, this is going to convert my temperature into something with units of energy, and as such, beta is going to be a measure of the coldness of my system, it's sometimes called. But since it's the gradient of this graph, right, this is the derivative of ln omega with respect to energy, and so this is equal to 1 over kt. The next thermodynamic quantity I'd like to talk about is the entropy of my system. And so given I have this probability distribution of all the microstates I have, I'm now able to describe this distribution with the entropy, which describes how sort of spread out all of my probabilities are. And so I'm going to say that S of a probability distribution is going to be equal to negative kb times the sum of the probabilities multiplied by the logarithm of each of the probabilities. That is, it's negative kb multiplied by the weighted average of the logarithms of each of my probabilities. And so given I have this formula, again at equilibrium, all of my states are going to be equally as likely when they have the same energy. And so S is going to be equal to negative kb. So if I've got omega different states, then at equilibrium, pi is just going to be 1 over omega, right? So then I get negative kb times the sum of 1 over omega multiplied by the logarithm of 1 over omega. This is just equal to the logarithm of omega times negative 1, so it's going to cancel out with this negative sign here. And all of this is independent of our iteration variable I, so we can bring it out the sum, and so we just get kb 1 over omega ln omega times the sum of 1. And in this case, I'm just going to be iterating over each of my terms and adding 1 to my total, so this is just going to give me the total number of states I have, which again is omega. That's going to cancel out with this, and so at equilibrium, the entropy of my system is going to be equal to kb times ln of omega. And so now I have this formula. You'll note that this ln omega was also seen in this derivative. And so if I multiply everything by kb, so I had this. Multiplying everything by kb, this kb ln omega is equal to s, and so I now have the derivative of this entropy function with respect to energy is equal to 1 over t. And so rearranging, I end up getting a way I can express the change in my energy is as T multiplied by the change in my entropy. And this term is what happens to be the heat in my expression. And so where I had du is equal to dq minus pdv plus the sum of my mu I d ni, I can now express the small change in heat as TdS. So yeah, this is the first law of thermodynamics, this expression here. And it talks about the different ways I can change the total energy of my system. But obviously, I'm going to transfer any energy I lose to my surroundings or to different forms. So anyways, going back to writing it like this, dw, actually, looking at this, if I've got a chemical reaction happening or a phase transition or something which would change the chemical potential energy makeup of my system, then if I keep my system at constant entropy and at constant volume, such that these two terms cancel out, then I would just be left with my change in my potentials. However, that's not always the case, and as we'll find, keeping entropy constant is quite difficult. And so this is at entropy and volume being constant. And so this is quite difficult. Differently, if I wanted to consider the heat change of my system, du is equal to delta Q, given that I keep the chemical makeup of my system and the volume constant. Now for a chemical reaction, oftentimes keeping the volume is quite difficult because I've often got gases produced which are sort of expanding everywhere. And so instead, what's quite useful to define is the enthalpy. So I say for H, the enthalpy is equal to U plus PV, such that when you take the derivative of H or consider a small change in H, dH, this is equal to du, which we can expand out, TdS minus PdV plus my chemical potentials, and then this pressure times volume can be expanded with the product rule to become PdV plus VdP. And now you can see that these PdVs are going to cancel out, and so now my new state variable H can describe the chemical potentials at constant entropy and pressure instead. So dH. When I'm at constant entropy and pressure. And it can also describe the heat change of my system, assuming I keep the entropy and the chemical makeup constant. So I've got this, and then also entropy is a bit difficult to change. And so the idea is if I've got a process which changes the energy of my system. So if I heat it up, or I let the gas expand, or if I close it down and I make the gas um, occupy a smaller space, I'm going to increase or decrease the energy of my system. And so what's going to happen to each of my energy levels is they're going to slowly change in size. Um, but they're going to stay roughly the number of states is going to stay roughly the same, and the amount which is occupied is going to stay the same. So if I had sort of 2 electrons occupying this state, and then I moved on to a lower energy state, these 2 electrons are still going to occupy the state, unless I have some sort of collisions or some other processes happening, which is going to excite them, or it's going to excite the particles. But anyways, if I do a process really, really slowly, it's going to give the energy levels time to adapt, and it's going to enable my electrons to fill all these states. And so all that's going to happen is I end up getting ds equals 0 if I do something really, really slowly. And so this is what's called adiabatic conditions. But it's quite hard to achieve and is a theoretical idea. And so instead of keeping entropy constant, we can do a similar thing to when we defined the enthalpy, and we can take U minus Ts to be equal to F, the Helmholtz free energy. Oops. And so again, expanding out, the differential of F is going to give you TdS minus PdV plus all of these. And then this TS term is going to turn into minus TdS minus SdT. And so these are going to cancel out now. And so I'm able to look at the chemical potentials if I look at constant volume and temperature, which is a bit easier to achieve. And I can also look at the work I'm doing if I keep the chemical makeup and the temperature constant. And so anyways, I want to go back to my partition function, which I defined, and derive expressions for each of these quantities, U, for U and F and S, in terms of this partition function. And so we had the definition, I'll write it again, that is the sum of e to the minus beta ei, so epsilon I, for each of the particles in my system. And so if I want to look at the internal energy, right, that's just sort of the average energy that one of my particles has, that my system has. And so I'm going to write the average like this. And the average of a probability distribution is just going to be equal to epsilon multiplied by the probability that my state, that my system is in each microstate. And so that's given by 1 over q multiplied by e to the negative beta epsilon I. And so the trick to this, well, I can take q out first, and then I'm also going to take a negative out. And so now inside my sum, I have negative epsilon I, e to the negative beta ei. And now you can see that I've got this negative epsilon I here, and I've also got a negative epsilon I here. So I'm going to move the beta to this side to make it a bit more clear. And so epsilon I is essentially a constant here, and so this is equal to the derivative with respect to beta, these should be partials, of e to the negative beta epsilon I. And I can bring this derivative out because it's a linear operator. And what you'll find is this sum is just Q. So you end up with this. And whenever we have a function, the derivative of a function divided by the original, this is equal to the derivative of the logarithm. And so this is just going to be equal to negative times the derivative of ln q divided by delta b. So by del b. However, this isn't actually the internal energy because we've sort of translated each of our terms by negative epsilon zero to zero our system, and so we're going to add back on our ground state energy here. So that's the internal energy. Similarly, the entropy, well, that's defined for a probability distribution, and if we plug in the Boltzmann distribution, then we're going to get, again, this is pi ln pi. So if we plug in the Boltzmann distribution probabilities, pi is equal to 1 over q, e to the negative beta epsilon I, and then the logarithm of this is going to give negative ln q subtract beta epsilon I. And so manipulating this a bit, this is going to give us ln q kb times the sum of 1 over q e to the negative beta ei, then plus kb beta times the sum of epsilon I over q epsilon I e to the negative beta epsilon I. And so for this first term, I'm going to replace these back with pi, and so the sum of all of my probabilities is just 1, and so that sum is going to just multiply out. And then for the last term I have, this is quite similar to what I had with my expected energy case, missing a negative, and so I can negate here, and then this ends up being kb beta times the expected energy. Okay. So now if we combine these, again we said F is equal to U minus TS, and so F is going to be equal to the expected energy. Oh, sorry, did I put a plus there or a minus? Yes, good. That's epsilon naught, and then I'm going to subtract T times this, so T ln Q multiplied by KB plus KB T beta. If you recall, beta is equal to 1 over KBT, so this term is just equal to 1 plus V. Oh, this should be an epsilon. And this is subtracted now. So these are going to cancel out, and in the end I get the expression F is equal to negative KBT ln Q plus epsilon naught. Okay. There's also a fourth potential. So when I had H is equal to TDS plus VDP plus my sum, right? Again, I don't really want to keep entropy constant. It's a bit weird to work with, so I'm going to define the Gibbs free energy, G, to be equal to H minus TS. And so expanding out, dg is going to give me, I'm not going to work through it, but it's going to give me negative s dt plus v dp plus the sum. So if I care about the sum, this is equal to dg when I keep my system at constant temperature and pressure, which are often the conditions I'm going to be using for chemical reactions. Okay. Anyways, we talked about the first law of thermodynamics at the start, sort of conservation of energy. And so the second law of thermodynamics is going to be about the quantity of entropy. And so when I go back to my first axiom, where I said that when a system reaches equilibrium, the probabilities of all my states are going to be equal. So that is pi is equal to 1 over omega. When this is the case, and the second law is going to say that when this is the case, it's going to imply that S is maximized. And so if I have S of P, right, I can say that the argument which maximizes this is going to be Pi is equal to 1 over omega. And so to prove this, we're going to take our function S is equal to this. And so we're just going to look at the first two states. And we're going to look at a perturbation from this equilibrium, and we're going to show that whatever we do, we're going to decrease the entropy slightly. And so the entropy for the first two states, well, the entropy is going to be equal to, if I write out the first two states explicitly, is going to be negative kb p1 ln p1 plus p2 ln p2 plus some other constants I don't care about. And here p1 and p2 at equilibrium are going to both be equal to 1 over omega. And I'm going to say this is just equal to a, because otherwise I'm going to be writing a lot of 1 overs. Yes, Shohan, you can have a shout out. But anyways, so if I have, if I say that P1 is now equal to A plus some perturbation X, and then P2, to keep the total probability equal to 1, is now going to be A minus X, then S is going to be negative KB times A plus X ln A plus X plus A minus X ln A minus X plus C. And now I want to show that x being 0 is a maximum, and so I'm going to take the derivative of this with respect to x. And so I can expand out this derivative. So here I'm going to get a plus x over a plus x plus then a plus x. This is just 1. And then here I'm going to end up getting a minus x over a minus x. Is that correct? Sorry, there's going to be a negative as well. So this is going to give me negative 1. And so these two are going to cancel out. And then the second term here is going to be subtracted of a minus x, and this plus c is going to disappear. And so combining these logarithms, actually that's not too useful. I'm just going to write this out more neatly. So I've got negative kb ln a plus x minus ln a minus x. So if I were to take the second derivative of this, I'll also just showing that at x equals 0, this is going to be equal to negative kb ln a minus ln a, so that's equal to 0. But looking at the second derivative, ds, over dx. This is going to give you negative kb, and then that's 1 over a plus x minus negative 1 over a minus x. So these are going to cancel out. So plus. So now when I evaluate this, x equals 0, I'm going to get negative kb, 1 over a, 2 over a, and so this is negative 2 kb over a. A is positive, and so this expression is going to be negative, and so at x equals 0, my system is at a maximum. So basically, my axiom that at equilibrium, my probabilities are all going to be equal translates to at equilibrium, my entropy is maximized. And so when I go towards equilibrium, any small change ds I'm going to have is going to be positive or equal to 0 in order to get to that equilibrium. And so entropy is an extensive quantity, and so we can, so again, if we have our sort of system and surrounding reservoir model, the total entropy of my system, and the total entropy change of my system is going to be equal to the entropy change of my smaller system plus the entropy change of my smaller surrounding. And this is also going to be greater than or equal to 0. And now, assuming I'm working at constant pressure and temperature, first of all, I'm going to say that ds of my surroundings is going to be equal to, a reminder that TDS was equal to delta Q, and so ds is going to be delta Q over T of my surroundings. And so to get the change in heat of my system, I can put a negative in front of it. Because my energy is conserved, and this is also greater than or equal to 0. And now, considering the conditions I'm in, I can put a different thermodynamic potential to represent delta Q, but again, for chemistry, the conditions we're going to be working with most of the time are going to be constant pressure, and so delta Q is equal to dH, and so this is going to be dH over T. I'm going to remove the sis's because I'm just going to say I'm referring to the system now. Now, if I multiply this by negative t, I'm going to end up with dH minus t ds is less than or equal to 0. And this, you might recall, is going to be dg at constant temperature. So anyways, I now get dg is going to be less than or equal to 0 for a process working towards equilibrium. And I call a process which is going to do this spontaneous. It's going to happen if I have sort of the activation energy to do it. Okay. Anyways, going back to F. So we said F was equal to epsilon naught minus kBt ln Q. And so if we want to look at all of the individual particles in my system and work out the chemical potential, right, since I had plus a bunch of other stuff, is going to be equal to df. If I can sort of work out the derivative of f with respect to ni, I'm going to replace these with partials, which means I'm keeping all of my other stuff constant. So essentially that's going to get rid of all of these and also all the other terms in my sum. This is equal to mu I. And so my goal is sort of to get this expression for f in terms of n. And the way I'm going to do this is I'm going to break down my big partition function Q, which is going to represent my total system, into the partition functions of multiple different molecules. And so um, where I have the energy of a particular microstate being equal to e to the negative beta epsilon I, this is further equal to e to the negative beta epsilon j times e to the negative beta epsilon I k. Oh, I guess I should replace these with like 1 and 2. Where the second index is representing the particle I'm talking about, right? Because if I multiply all of these indices together, I'm going to end up with a sum here, which is the total energy epsilon I minus the 0-point ground state. And so I guess a naive guess would be to say that Q is equal to little q to the power of n, where little q is the partition function of each of my individual molecules. However, this ends up being wrong because for a given microstate, I don't particularly have an order to it. And so basically, if I've got like 2 energy levels here, I don't care about whether particle 1 and 2 is here, or whether I have particle 1 here and 2 here. And so I'm going to end up dividing by n factorial. And this is for n identical particles. And similarly asking the same question is just going to end up with like n1 here, and then you multiply like that for each of the different types of particles I have. And so if I were to input this into F, I can use my logarithm rules to break this up. And so what I'm going to end up getting is n1 ln q1, q2 ln q1 divided by factorial, which we can further bring out as a subtract ln n1 factorial plus a bunch of stuff about n2, n3, so on. And so we're going to use Stirling's approximation again, which is a reminder, ln x factorial is approximately x ln x minus x, and so you're going to get epsilon naught minus kbt n1 ln q1. I guess we can replace these with I, because we're talking about like a given type of particle. And so this ln ni factorial is going to become ni ln ni plus now ni. And so now we have this expression for f, and so we can take the derivative of this with respect to ni to get our chemical potential. And so the first thing I'm going to get is this derivative, and I'm going to call this the ground state energy of a particular particle type I, and so this is going to be epsilon naught comma I, and then I'm going to get in here, subtract kb t ln qi, and then plus I've got to differentiate kbt ni ln ni, so this is going to go to kbt and then plus kbt ln ni, and then I'm going to get minus kbt here. And so these two terms are going to cancel out, and we can combine our logarithms to get the formula mu I is equal to epsilon naught of I plus kbt multiplied by the logarithm of ni over qi. Now, recalling that we're working at constant, if we change our conditions to be working at constant temperature and constant pressure, so those are the conditions in which the Gibbs free energy the change of the Gibbs free energy will just yield the sum of the changes in our potentials, right? We have dg is equal to the sum of mu I n. Sorry, dni. So anyways, we're going to look at an example chemical reaction. So for example, if we have two lots of A goes to B, so we have some dimerization. For example, this might be, I don't know, two chlorine radicals terminating to form a chlorine. What you would see is if I have some arbitrary variable representing the reaction progress, dx, the change in the number of A particles I have is going to end up being -2 times dx, whereas the change in NB is going to be just dx. And so if we take that small step, we get dg is equal to the sum, I'll just write out the sum, mu A times -2 dx plus mu B times dx. And so the dg for a reaction is always going to be less than or equal to 0 if we want to move towards the equilibrium. And so if we take a graph of g against reaction progress, equilibrium is going to be at this maximum value when dg is equal to 0. And so if I write out the form of my chemical potential, right, as, so this is epsilon naught A plus kbt ln n A over qa. Na is going to get a bit confusing because there's the same symbol for Avogadro's constant, so I'm going to swap to moles now. So I'm going to replace Na with a different Na times a different Na, a bit confusing, but so this is the number of my particles A, this is Avogadro's constant, and this is the moles of A. Right, so if I replace this with little n A times Avogadro's, so that times -2, I'm just going to divide by the dx's now, plus epsilon naught B plus k b t ln and B times Avogadro's over QB. I'm going to say that's equal to 0. And so I'm going to get two different types of terms here. I'm going to get my epsilon terms and then these ln and over q terms. And so anyways, I'm going to combine the epsilon terms into some overall change in ground state energy for my reaction, delta epsilon naught. And then for these terms, I end up getting -2 kbt ln over qa plus kbt ln b na over qb. And so combining these two together is going to end up giving me plus kbt times the logarithm of nb na over qb multiplied by qa squared over na squared and a squared. This can cancel out here, and combining these is going to overall give us delta epsilon naught plus kbt ln of nb QA squared over QB NA squared times Avogadro's is going to be equal to 0. And so we've essentially derived a formula for something which stays constant once I reach equilibrium. And so a useful thing to define is the equilibrium constant. And so I'm going to say that K is going to be the ratios based on my sort of reaction stoichiometry. And so K is going to be equal to NB over NA squared, right? So essentially when I had 2A goes to B, I'm taking this raised to the power of its stoichiometric coefficient divided by this raised to the power of its coefficient. And so to get this K, sorry, I think I've done something wrong. Oh, I forgot a negative, sorry. So I've got this negative here. And so this should be, oh no, that's fine, sorry. Oh no, it's fine. And so anyways, I can subtract epsilon naught from here. And so I get negative epsilon naught, delta epsilon naught is equal to kbt times this logarithm. I can divide by kbt now, and then take the exponent. And then if I cross multiply out by QB over Q A squared and NA up here, I'm going to end up getting K on this side. So yeah, I have this formula for this constant of equilibrium. And so in the next episode, I'll go about how you'd calculate this and how you'd calculate the partition function for different scenarios. And then, yeah, that's pretty much it. Thanks for tuning in. Sorry it was a bit rushed. Hope you enjoyed.